Fubini's theorem offers us some flexibility in how we compute iterated integrals. It says if f is continuous, you'll notice there's a star on continuous, I'll come back to that later. If f is continuous on the region R, which is the set of x, y, such that x is between a and b inclusive and y is between c and d inclusive, then the iterated integral, or the double integral, over R of f of xy dA is equal to the integral from c to d of the integral from a to b of f of xy dx dy. Now that's not new, but Fubini's theorem says that the order of integration can be reversed. That is to say, the integral equals also the integral from a to b of the integral from c to d of f of xy dy dx. For the little star on the word continuous, this holds if f is bounded, which means finite, and has a finite number of discontinuities. Much like single integrals. And much like single integrals, if z, which is given by f of xy, is greater than or equal to 0 on the region R, then the integral can represent a volume. Furthermore, this is not Fubini's theorem, but if f of xy can be factored, say f of xy is equal to g of x times h of y. So if we can factor it into a function of x times a function of y, then the double integral over the region R of g of x h of y dA can be computed as two separate integrals, the integral from a to b of g of x dx times the integral from c to d of h of y dy, where R is equal to the rectangle given by the closed interval AB on the x-axis by the closed interval CD on the y-axis. So how does this work out? Well, for the rationale, in the integral from c to d of the integral from a to b of g of x times h of y dx dy, h of y is constant with respect to x. So this becomes the integral from c to d of h of y. It's like, as a constant, it can be kind of factored out of the inner integral of the integral from a to b of g of x dx dy. But in the same way, the whole integral from a to b of g of x dx is constant with respect to y. So we can factor out that whole integral as a constant, and we have the integral from a to b of g of x dx times the integral from c to d of h of y dy. This can come in handy because now I can evaluate both integrals in one step, whereas with an iterated integral, I would first evaluate the inner integral and then evaluate the outer integral.